Hey everyone, welcome back to section 7.1, where we're going to be looking at testing goodness of fit for a single categorical variable. All right, so we've looked a lot at categorical variables so far. For example, in section 6.2, we looked at tests for a single proportion that deal with a single category from a categorical variable. But in chapter 7, we're going to look at methods that are going to allow us to test for two or more categories here at the same time. So to do this, we're going to use the so-called chi-square goodness of fit test. Chi-squared is notated by this character here, that big kind of X is the Greek letter chi. So let's start with this first example. We have a large bag of fruit-flavored candy with 5 flavors in the bag. The company reports that the bag should contain an equal number of each flavor. We'd like to test the company's claim that the proportion of the 5 flavors are the same. Our bag contains 1,000 pieces of candy, so this is our sample. The results are shown below. So we have the observed count for each flavor and the observed percentage right below it. So the count of apple, for instance, is 180 candies or apple. That accounts for 18% of the total. Now, if the company's claim is correct, we would expect to have equal numbers for each flavor. In this case, that means 200 pieces of each flavor is what we expect. Now, below you can see the actual values that we observed against that value of 200. There's a little dotted line that goes through it. So a couple of the flavors are less than 200, a couple are more. Now, without doing any statistics at all, we can see that the number of pieces for each flavor are not the same, right? Now, even though we expected 200, we're not really surprised that they're not exactly 200, right? We know through random variation to expect different values here. The question is, how far away from 200 are our values? Are they so far away that we have evidence that the company is not being truthful? Or our values are close enough to 200 so that it could be due to random variation? Okay, so to test this, we need a test statistic, right? We've done this with single proportions, difference of proportions, single means, and so on. We've used single test statistics to find p-values. But what's the statistic here that we would test? Remember, we're looking for a single statistic. So this is what the chi-square statistic does. It gives us a value to test multiple categories. So looking at the box here, the key question is, are the observed counts in the original sample farther from the expected counts than we would reasonably tend to see by random chance alone? Okay, so here our expected counts are 200, and the observed counts are the values for apple, cherry, grape, lime, and orange. So are those differences larger than we would expect due to random chance? Okay, so the statistic that we're going to use to test this is the chi-square statistic, and it is computed like this. It is a sum of the observed counts minus the expected counts squared divided by the expected counts. And this is a sum over all categories. So here we have 5 categories. So we would be adding up 5 values. Right, so we would compute all of this for each category. So we're taking the difference in count between the observed value and the expected value and squaring that value and then dividing by the expected count in that category. Then we do that for each category, add them up, and that is our chi-square statistic. All right, so let's find the chi-square statistic in this problem. All the 5 categories, we're going to add the observed minus the expected squared divided by the expected. So I'll call that OA minus EA squared divided by EA. And then we do the same for cherry and grape and lime and orange. All right, so here I'm going to set the first calculation up for apple, and then I'm going to let you try the rest. So the observed value for the apple flavor was 180. expected for all of them are 200. Then we're going to square that difference and divide by the expected value, and that's the calculation for each. So you go ahead and pause and try here, fill in the rest of the values for the different flavors, make that computation, and then come up with the chi-square statistic, and press play when you're ready. Okay, so here I've just filled in the observed minus the expected values using these chi-squared formula. We call each of these values the contribution to the chi-square statistic. So if you compute the first value for apple, 2 is the contribution. Cherry, the contribution of cherry was 32. You can see because cherry was so much further from 200, it's much larger than the contribution from apple. Grape, the contribution was 3.125. And our contribution from lime was 12.5. And then orange, same contribution as grape because they were both 225 observed values. So I'm just putting these in my calculator. I'm taking the difference in the numerator, I'm squaring it, dividing by 200. And if I add all these up, I get 52.75. And that is our chi-square statistic. All right, since this is the first time we're calculating it, we really have no way of judging whether this is a big number or a small number. So we're going to find, the next step is finding out if this is indeed an extreme statistic, or does this indicate that our observed values are close enough to the expected? Now that we have our test statistic, we're going to formally state the hypotheses, and we're going to test them. So first, what proportion do we expect each flavor to have if each flavor is represented equally? A proportion of 0.2, right? 1 out of 5. All right, so my null hypothesis is that PA, it's the proportion of candies that are apple, is equal to PC, which is proportion of cherry, which is equal to grape, which is equal to lime, which is equal to orange. The proportion of all those are all equal, and they're all equal to 0.2. Now the alternative is not that they're all different. It's just that one of the proportions is not 0.2. So our alternative is some PI, I'll tell you what that means in a second, is not 0.2. Now I, it just stands for one of these. So our alternative is we're just looking for evidence that one of the proportions is off, basically. We're not looking that all of them are off. Okay, so this is the setup. So you can see how this is a bit different than our typical single proportion. So now, as in chapter 4, what we want to do is see what kind of statistics would we expect to see given the null hypothesis is true. Now remember, the statistics here are chi-square statistics. So what kind of chi-square values would you see if all the proportions are equal? That's what we need to see before we judge how extreme our chi-statistic of 52.75 is. So this is something we need to go to StatKey to do. So the first thing we do is we go to the StatKey page and we go down to more advanced randomization tests. And here we are at chi-squared, goodness of fit, and I get this screen. So we want to edit the data to match our data. All right, and here I have a header row, so I'm going to leave that box checked. And here we have our data, and you can see that statistic is confirmed. On the side, you see that under the original sample, chi-square is 52.750. And what I want to do is generate a few thousand samples. We'll just call it maybe 5,000. Here's my 5,000 samples. Those, I want to recognize each one of these dots on this distribution is a chi-square statistic generated under the assumption that all the proportions are equal. Right? So if you want to run you want to check these values on the distribution, you can see the randomization sample on the bottom shows you some of these statistics that we'd expect to see. And you can kind of explore what kind of observed counts we would have if the proportions were coming from a population of equal proportions. And you can see in general, they're all a lot closer to 200 than the ones we observed. All right, so the other thing that I'm not mentioning, which is probably jumping right out, is this is not a bell-shaped symmetric curve. Right? This is a big right. Has a heavy right skew. This is a characteristic of most chi-square distributions. So that's new to us. So we're not expecting symmetric distributions here for chi-square. All right, so now we do what we did before. We look at the values on the horizontal axis and we see that our value of 52.75 is nowhere to be found here. It's not even close, which means with 5,000 chi-square statistics, we did not observe a statistic even close to the one we found. So then we make that conclusion that it is extremely unlikely that we would observe a statistic as extreme as 52.75, assuming our null hypothesis is true. In other words, that all the proportions are the same. All right, so this looks like very, very strong evidence that these proportions are not equal. So we go back here and we're asked to kind of sketch that picture. And number 4, they're asking us how likely it is to find 52.75. Well, I can already tell that it's 0, right? But it says to, click that right tail, and you can see that there are clearly no proportions more extreme than that. And we saw a p-value of 0 here, which means it's virtually impossible that this sample could have come from a population where the candies all had an equal proportion. And then finally, we're asked to make a conclusion using an alpha of 0.05. So this works the same way. So since 0.00 is less than 0.05, we reject the null. That is, that the proportion of candies is not equal. The proportion of flavors are not all equal to 0.2. All right, so let's just recap what we did here. We did a randomization test for goodness of fit. We assumed that the population was composed of different types of categories and the percentage. So for our example, we assumed that all the proportions were 0.2 for all the flavors. Okay, so that's what we started with. Then we took many, many samples. This was what StatKey did this, from the population. And each time we record that statistic. And then finally, we look at that randomization distribution and we look how extreme our chi-square was from our observed values. In our case, we had 52.75. And then we noticed that statistic was very extreme based on the p-value. That basically there were no statistics more extreme than 52.75 under the assumption the null is true. And then the conclusion is the same. It is no different at all. The formulation of the null hypothesis might be slightly different because it has to do with multiple categories, whereas in before we were just talking about one category. But other than that, that's not different. That won't be different for us here using chi-square than any other statistic. Okay, now we learned in chapter 5 and 6 that you can also use theoretical distributions. And by that I mean the normal or the t distribution, instead of relying on these simulations, which we just saw the randomization distribution is a simulation. And there is a theoretical chi-square distribution that we can use. All right, so the model of a chi-square statistic is dictated by the degree of freedom, which is k minus 1, where k is the number of categories being considered. And there is a test for sample size. The sample size is each of the expected counts. All right, so luckily that count is very low, which means this distribution is very widely applicable here. So for a hypothesis test, the statistic looks like is the chi-square statistic, and that is the sum of the observed minus the expected counts squared over the expected count for each category. If you're familiar with the summation notation, we're saying we're adding up each one of these observed minus expected squared divided by expected from the first category to the nth category. So if you're not familiar with that summation notation, you might just want to think of the sum this way, written out and expanded, right? So you're just taking the sum of these observed minus expected values squared, that's your numerator, divided by the expected value. And so you do that for each of the categories that you're looking at. Okay, so then it says to use our theoretical chi-square distribution to find the p-value of our test statistic. Okay, so let's go back to StatKey. And notice here we have theoretical distributions towards the bottom of the screen. We hit chi-square, and then I go to my degree of freedom here, which now degree of freedom is the number of categories minus 1. So in our problem, I had 5 categories. So my degree of freedom was 4. And if you remember, the distribution looked a lot like this curve here. It kind of peaked out around 2 or 2.5, started tailing out around 10. So this looks very similar. We can do the same thing. We can hit right tail. We can test our value of 52.75. And you can see a very similar picture, except this one has a smooth curve drawn instead of piles of dots. But we see a very similar picture. So the sketch was something like this. 52.75 gave us a p-value again of 0.000. And so you can compare that to our picture before. It looked very similar, right? So it's we expect our theoretical distribution to look similar to the randomization distribution, and it does. All right, so again, we know we have these 2 methods for finding p-values. We have our theoretical distributions we learned in chapter 6. In chapter 4, we had our randomization distributions. These are equivalent methods. The simulations are there to help us understand what the theoretical distribution is actually estimating, right? And so if you're not asked to do one of these in particular, it's up to you, but often the homework problems will ask you to do one or the other. So just make sure you're understanding what they're asking you for there. All right, so I'm going to cut this video here, and in part 2, we're going to look at a case where all the proportions in our null hypothesis are not the same. So I'll see you in that one.